I'm Orit Wasserman. I'm distinguished engineer in IBM, and I'm leading the architecture of the NVMe-oF Fabric Gateway. And with me is David Carroll, who is the NVMe-oF Fabric engineering manager at IBM. So let's start. What is this NVMe-oF Fabric? We all hear the name all the time. So NVMe is not new anymore, but used to be a new way to consume storage from your local SSD. NVMe is non-volatile memory, express because you actually access the device through PCIe Express. It's a modern protocol based on lots of queues. We have submission queues where you submission your request, completion queue where you get the response, and also admin queue for the control plane. And when actually the first time I looked at the protocol, it looks very familiar. Anyone who sees knows a bit NVMe, what other protocol does it look like? So first of all, it looks like a network protocol, not storage. Queues, we don't do much queuing in. Also, I came from virtualization, so this looks like Virtual, very similar. And also, anyone who knows RDMA, very similar to RDMA with the queue pairs. So actually, it makes sense. Why not we extend that protocol for consuming local disk to be on top of the network on some fabric? And it's actually was relatively easier to extend it, not like iSCSI. And the first fabric this was implemented for was RDMA. Yes, which happened. And then later, many customers for storage have a fiber channel network. Why not consume NVMe over fiber channel? And the obvious step is why not use the most common fabric in our data center, TCP. It's everywhere, easy to configure, we all use it all the time, and for Ceph, it's natural. So it was actually works for the company, invented NVMe TCP, and it was ratified quite quickly, less than a year, in 2010. It's been ongoing, and it's become very, very common ground. What's good in NVMe-oF Fabric, it's very also easy to offload to hardware, to use DPUs, IPUs, accelerators. So, that's first question. Who here uses Ceph iSCSI? Oh, my. Yeah, so what? So we have Ceph iSCSI Gateway, been for a while. Why not? Isn't it enough? Why do we need a new gateway for another access storage on the TCP network? And so on, as I said, NVMe is more modern. Scales much better than iSCSI. Performance-wise, you usually will get much higher performance with NVMe-oF Fabric compared to iSCSI with the same hardware. And it's not only more IOPS and reduces latency, it also uses less CPU. That's true for the gateway, we use SPDK, but that's true in general. And it can scale. You want more queues, you have enough cores, you can spin up as many queues you need. So you can scale and consume storage really fast devices. And why do we want NVMe-oF Fabric itself? So it's similar to iSCSI, the same reason. The main one is VMware. With VMware, I cannot use RBD. They will never support libRBD or KRBD. I need to use standard industry protocol. So one option was iSCSI. Now you can also use and implement NVMe-oF Fabric. And as I said, NVMe-oF Fabric, with NVMe-oF Fabric, it's much easier to use hardware acceleration, to offload the TCP, to offload compression, encryption, and many vendors, hardware vendors have very nice hardware. It's Sandoz, NVIDIA, Intel, and so on. So let's look how gateway. So first of all, about NVMe, every protocol needs to be special. So NVMe doesn't have LANs of volume. We call them namespace. I don't know why. That's what Stalin decided. So an NVMe namespace map to one-to-one to an RBD image or a volume to say. And then when we want to group namespaces, we have a subsystem. A subsystem is a logical group, and the host initiator will connect to a subsystem, and we see all the namespaces in that subsystem. And we can do access control per subsystem using NQN, which is that NVMe identifier we already. We're going to support different types of initiator. Currently, we tested Linux with initiators, well, Ubuntu, and ESX initiators. So how do we deploy the gateway? So the gateway is a container, like every other Ceph daemon. And you can run it, we prefer to collocate it on the OSD nodes, but if you need more CPU or want, you can actually run it on a dedicated node. And you have several gateways in the cluster. Currently, we support only one gateway per node, so implementation limited. Next version will support more. And then you can actually configure the initiator to access different namespaces, different subsystems, and as I said, we support both Linux and ESX. So what is in this container? So we have two parts. The first one is the control plane. We need to configure the mapping between the namespaces to the RBD image, access control, and the J that Aviv is going to talk later. All those we need to configure. All the control daemon store the config as an OMAP. Who here knows what OMAP is? Yes. So OMAP is a special object in Ceph. It's a key value store that we store inside of Ceph, inside of Wireless. And we use it a lot, for example, in RGW. Someone talked about there was talk about the problem with garbage collection of objects. The GC list was an OMAP. The bucket index is an OMAP. So an OMAP is a very strong type of object in Ceph. We store the config in an OMAP, and we all use all the gateways in the same group, store the same configuration, and can access the same configuration, and it's persistent, replicated, everything by Ceph. So this is cool, and they can use another mechanism, watch notify, to get to know when the configuration is updated. So basically, all the gateways see the same configuration, and if you change, they get a notification that there is a change in configuration. How can you configure the gateway? So we have our own CLI. Currently, it's a separate container. We are changing that. Next version, it will be a Python package. And for the future, we want to integrate it into the Ceph CLI as a first-class citizen. And you can use gRPC. And also, you have the Ceph REST APIs. All those allows you to configure the gateway. And the CLI and on the REST API, you can use MTLS, mutual TLS, for authentication and encryption. Let's talk about the data part. So I actually implemented a few years back, part of the team, it was a large team, an NVMe-oF TCP target. That's quite complex. But we are open source. Is there a open source project that has a target? So yes, luckily for us, we have SPDK. SPDK is much more than a target. SPDK is a really cool tool. It's an open source project started by Intel, but today they have many contributors, but Samsung, NVIDIA, I don't know, the list is long, Red Hat. It provides a very a framework to do really efficient storage I/O. It uses a reactor model. We had a Crimson talk using C-Star. C-Star is also a reactor model. So it's very asynchronous. And someone from Intel already implemented support for LibRBD. it has an abstraction called BDEV, block device, and you can put under the target whatever storage. You can actually do NVMe over Fabric on top of HDD if you want to, but you can also do it on RBD. So basically, someone already did lots of lifting for us in the open source community. That's the power of open source. So we are using SPDK to implement all the data. So in our container, we have the control daemon in Python, and we have SPDK running as well. And the control daemon uses locally RPC commands to talk with the SPDK. And SPDK implements all the NVMe over Fabric commands for us. So when the initiator basically connects to the cluster, we will connect using NVMe connect command. We will go to SPDK. So most of the commands for NVMe we already have in RBD. So read, write, that's clear, unmark is like delete, flash. And the one we had to change were compare and write. Compare and write is used when two different applications want to use the same NVMe namespace. So you want to make sure they don't corrupt the data. ES6 uses lots of compare and write. There was an initial implementation of compare and write in libRBD, but it was for very small block size, a few bytes, and we had to extend it. And then currently we use emulated command. That means SPDK does them, not libRBD. They don't go to libRBD. Compare is done by SPDK copy, which will probably in the next version, future versions, will offload to libRBD to be more efficient. And abort is special. NVMe has an abort command. So why it's special? One, the original implementation of NV abort has many problems. One of them, it goes to the admin queue. So in spite of the fact that it's an IO data path command, it actually went to the control plane, to the admin queue. So now there's a new command called the NVMe cancel, very new, and that will go in the data path and go to the submission queue. Another issue, libRBD doesn't have a way to cancel or abort a command that already was sent to the OSDs. So what we do in abort, if it's still in SPDK, we abort it, take it out of the queues. If it was sent already out, we basically cannot abort and we fail the operation. And Linux, for example, initiators don't use abort because of lots of issues. I'm going to use one day cancel, but currently just reset the controller. Reset controller means you basically start the session from the beginning, disconnect and connect to the target. Discovery is another very cool feature for NVMe-oF Fabric. So if you want to, when you connect to the target, you can say the IP port of the target you want to connect. But we are clustered. We have lots of targets. Each gateway is basically a target. So to make life easier, we have Discovery. NVMe has a command called connect all, where you connect, basically it runs Discovery, get a list of all the target IP and connect to all of them. You always want to be connected to all the target because if you have failure, which Aviv will talk more about, you will basically automatically move and consume IOs for a different target. ES6 is a similar command. I highly recommend to use those commands and not do connection manually. So Discovery service needs to be always available and always up. We have many gateways. Why not run it on all gateways? Why should we have to do a J? So we have a Discovery service now running in each gateway, and you can access any gateway to get the list of targets and IP. As the configuration is shared, it's an OMAP. All the gateways know the same configuration. They know the cluster state. So they always will return the same information. And yeah. Another thing, for VMware, VMware is the main use case. So VMware has a set of commands you have to have support for in order to be compatible with VMware. The atomic compare and set, which is compare and write, xcopy, which is copy, write 0, and then delete. We support all of them, and we work well with VMware. Another thing we got for free from SPDK and related to the previous talk, quality of service. You may want to rate limit initiator access to a namespace. So SPDK provides that for us. We are lucky. SPDK already has support for limiting. You can define maximum IOPS per second or megabyte, and even read and write megabytes per namespace. And the only thing you need to understand that it's not cluster QoS, it's for a single gateway. So if for some reason we don't allow it for a J, but if for some reason you will access the namespace from different gateways, QoS it will be per gateway. And currently no plan to do it distributed. I think the previous talk can convince you how complex it is to do distributed QoS. And now for the main feature for the version, availability.
Thank you. So I'm Aviv. I joined Ceph about 1 year ago. I'm leading the NVMe-oF over TCP in the last year. So I'm going to talk about high availability. Okay. So we have a concept that is called gateway groups in NVMe-oF. Right now, what we support upstream is one gateway group. And actually, gateway group defines the high availability domain. So you can fail over between gateways in the gateway group. So this is what we see here in the slide. So to have high availability, we actually must have at least 2 gateways deployed in the Ceph cluster. And what we currently tested and support, I mean, it's not hard-coded, but we support 4 gateways in a gateway group. But in theory, the code supports much more than that, and we're increasing scalability as we speak. So in a gateway group, all the gateways read the same configuration, the same OMAP file that Orit talked about. So every change that we are making to the OMAP file, like if we add a new subsystem or we add a new namespace, we can do it through either one of the gateways, but all other gateways will immediately be aware of this change and will update the local SPDK. Okay, SPDK is local to the gateway. One SPDK doesn't know about the other SPDKs, but we are making this connection through the OMAP so that every configuration change is reflected immediately in all the gateways in the group. Configuration, as Orit said, can be done through the CLI that we have, or through gRPC API, or Ceph REST API. So, from the host perspective, from like Linux, what you can see on the right side is Linux. So you're doing, for example, NVMe connect all. You provide the IP address of one of the gateways in the group, either one of them. And the connect all command is actually going to this IP address, doing discovery, getting the list of IPs of all gateways in the group, and automatically connects in a multipath to the gateway group. So you can see the multipath here. All the IP addresses, each IP address is a different gateway. And below you can see a new Ceph command that we added, and that you can see how the NVMe-oF monitor, I will talk about the NVMe-oF monitor in a minute, how the NVMe-oF monitor sees the status of the gateways. We'll talk about it soon. So in terms of the namespaces that we manage in the gateway group, every gateway at any certain point in time is serving only one of the namespaces. So I would say it differently. Every namespace is being served only by one of the gateways at any point in time. So all the namespaces are active on all the gateways, but at any point in time, some namespaces are optimized or served by gateway 1, others are served by gateway 2. We are doing it in a load balanced manner, so the namespaces are automatically assigned load balanced across the gateways. And in a case of a failover, we automatically move the responsibility of a namespace which belongs to a failed gateway to another gateway. This is being done seamlessly during failover, and if the gateway is coming back, we're failing back the namespaces to the original gateway that was assigned to these namespaces. Yeah, so we can talk about this one. Okay, so how do we implement HA? There are many ways to implement HA, and we had many design options, but we are using a concept that is called ANA in NVMe, asymmetric namespace access. So in ANA, you can define groups, how many groups that you want, and each group you can define if this group is accessible right now to the host or inaccessible to the host. So what we actually do is you create namespaces, and we allocate an ANA group ID for every gateway in the group. Like for example, in this case, we have two gateways deployed. We defined 2 ANA groups, and like for example, ANA group 1 contains namespace 1, 2 until n, and ANA group 2 contains the other namespaces. So in the eyes of the first gateway, these namespaces 1, 2 are inaccessible, but you can access these namespaces from the other gateway, and the other way around for the ANA group number 2. So these namespaces can be accessed from ANA group 2, but cannot be accessed, from gateway 1, but cannot be accessed from gateway 2. And if you adding more and more gateways, automatically we add more ANA groups. And so the game of HA is really about playing with which ANA group is accessible right now and which ANA group is not accessible. So for example, in the case that, I don't know if I have a slide for that. So in the case that gateway 2 for some reason failed, so we will see that automatically the optimized will move to ANA group to ANA group 1 on this gateway, and you will be able to access all the namespaces to gateway 1. If it's coming back, we are returning the state to the way it was before. Anything that I missed? Okay, so to implement this failover, failback, and game about ANA groups, we added a new monitor to Ceph. It's called the NVMe-oF monitor, and I have a slide about it. Yeah. So in very high level, it looks this way. So this is a new component in Ceph. It's called NVMe-oF monitor. In the gateway, in the NVMe-oF gateway, we added a monitor client. The monitor client actually sends beacons every 2 seconds to the NVMe-oF monitor. So this is the way that the monitor knows which gateways are alive or which gateway failed and we need to do failover. We defined a new map for the monitor. It's called the NVMe-oF map. And in the map, we actually tell the gateway, you need to be optimized right now on HANA Group 1, you need to be inaccessible right now on HANA Group 1, and so on. And the monitor is the one that decides that it's time now to do failover, or it's time now to do failback. So about the failover, how do we do failover? If the monitor, the NVMe-oF monitor decides that one gateway failed, it's time to do failover. So first thing that we do is setting the failing gateway to inaccessible. Whether it's it or not, we don't care about it. And second thing that we do is we are using the RBD block list. So we are making sure that all the namespaces that were accessible from the failed gateway are blocked. Nobody can write to these gateway to these namespaces from that gateway right now. We are making sure that the taking over gateway is getting the map with the new epoch to be sure that it's not going, that nobody else is going to be able to write from older epoch to these namespaces. And we assign the HANA group, like we could have many HANA groups if it's a big cluster, so we choose the gateway with the less number of HANA groups right now which are optimized. And then we set the HANA group to be optimized on the taking over gateway. So this is in very high level how we do the failover. Yeah, so I just want to mention here, so we are doing failover, failback only in the cases that the gateways are going down, right? But from the host perspective, if you have only one switch to the gateways, it's not good enough. You need to be sure that you have enough redundancy in the network because the HA is not taking care of this part at least. I'm telling this because I heard people being confused about that, so I think it's important to note. That's it about HA.
So currently the monitor PR is still work in progress in upstream. Hopefully we'll make it really complete, yeah. And what's next? What's next? So as I mentioned, we want to put the CLI as part of the Ceph CLI. We don't want a separate container, and we want the full experience. And something very important is the NVMe inbound notification. The NVMe has a way to authenticate. We're going to support that in future releases. And as I said, you can do access control per subsystem, but most users actually sometimes want more granular and doing per namespace access control that we call namespace masking. That's also in the plan. And basically everything about scale. So we have one gateway group, we want more, and more gateways in the cluster, more gateways in the node, more subsystem, more namespace, everything about scale. And always we want to have better performance, more efficient, less CPU usage. And it's very important to say thank you for everybody who's helping with upstream on the NVMe-oF fabric. For many companies, from IBM, we have IBM Research and IBM Engineering, and lots of help from SPDK community, so I want to thank everyone. And we want you to join our community, our efforts, even just to get feedback. We try the gateway. We have the gateway code, and we have a weekly meeting, upstream meeting, every Tuesday at 7 a.m. Pacific. We're happy to hear from you, and so thank you.
Yeah. Well, I have one about. Thank you. You initially mentioned about the fabrics thing. Are there any plans to support other fabrics besides TCP?
Oh, so I got that. So SPDK actually supports NVMe over RDMA over walking. The problem with Ceph RDMA support is seldom there. I'm not sure it's actually working now. Do anyone knows if it's compiled? Like last time I tried, there were build issues. And Ceph is not optimized for RDMA. I think with Crimson and C-Star, you can look at Ceph with RDMA, and then it makes sense also.
I think it's not being adopted. It's not really being adopted. NVMe over FC is not really being adopted by the industry, and the RDMA also. And for RDMA, you need special equipment, right? It supports so.
Yeah.
I don't think it's a high priority.
Thank you.
More questions?
Yeah. Thanks.
So as far as I understand it properly, the multipathing allows one active path at any time to any namespace. So we don't would be able to scale across multiple connections for a single namespace, right?
For a single namespace, you only have one. I mean, you can have 2 ports on the gateway, right? Two Ethernet ports on one gateway, and then it will go to the same namespace.
Okay,
but across the gateways, you cannot do more than.
So the scale out of the number of gateways would only just help for multiple namespaces in parallel.
Yeah.
Right.
But that's most of the people have lots of namespaces.
Yeah, just to understand it properly. Thanks.
Why do we need a dedicated monitor within Ceph? What is lacking from the existing one?
It's not a dedicated monitor. Inside of Ceph monitor, we actually have several monitors. Basically, it's an additional Paxos service. It's not a new monitor.
So it's a sub-component to the existing one.
Yeah, we have one from the MDS, there's one from Manager, there's one, of course, for the OSDs. There are like 8.
Got it. Thanks. And why does the interval needs to be like every 2 seconds if it takes for failover to take like 15 seconds you mentioned? So is 2 seconds arbitrary?
It's arbitrary.
Yeah.
It's configurable.
You don't
15
need
seconds is like maximum we can configure this too, but I
You
think
don't-
we're trying to stay way below 30 seconds, which is typically the host timeouts.
Got it.
But
Thanks.
So you mentioned that iSCSI can't be used with VMware, but NVMe is better suited for VMware. Just wondering why that is.
It's more about the iSCSI gateway implementation, but yes. So iSCSI gateway implementation, it's basically we don't have anyone who's maintaining it. Like India helps, but I think we lost the maintenance a few years back. It's about the implementation, the choose TCU. Lots of issues with the actual implementation. It's not that iSCSI is not good. It's Ceph iSCSI only. In general, iSCSI has a scaling issue. In general, as a protocol, it's actually. So NVMe over Fabric will scale much better and show graphs that usually iSCSI starts in 2-digit numbers, and NVMe you can always add more cores, more queues, and scale as much as usual.
Thank you both very much.